Hello everybody, how are you doing? Today we will learn some well-known discrete distributions. So we start with the first well-known discrete distribution named discrete uniform distribution. So we consider a random variable x that take n different values, say x1, x2, and so on and xn. And we suppose that the probability that x equal to some xi is 1 over n for any I. Then the distribution of x is called the discrete uniform distribution. Here is an example that we already studied this example in the previous section, but now we look at this from a different point of view. Now I have a box that contains n cards, in which there is only one red card. A student named Phương randomly draws one by one card from the box until she gets the red one. And remember that when she takes one card, she looks at the color, and if it isn't red, she put it aside. She put it outside the box and continue to take another card. And let x denote the number of cards which have been drawn. Then here's an exercise for you. You show that x has discrete uniform distribution, and compute the expectation and variance of x. Okay, so you have already learned this example when we study the multiplication rule of conditional probability. And now we look at that lesson again and try to solve this example. The second well-known discrete distribution is the binomial distribution. So we start with a simple example as follows. We toss a fair dice 3 times. You remember what is a fair dice? It's a die with 6 faces, and the probability that 8 faces show is 1 over 6. And let x be the number of 6 obtained. Find the distribution of x. Okay, so x is the number of 6 of the die when we toss it 3 times. So x can take value from 0 to 3, right? And we denote x1 is the event that the die shows 6 as the first rise. x2 is the event that the die shows 6 as the second try, and so on. So we have x1, x2, and x3. And now, when x equals 0, what happened? X equals 0 means that all the time means that each time we obtain the face, so we show 1, 2, 3, 4, and 5. It means that P of x is 0 equal P of complement of h1 intersect with complement of h2 intersect with complement of h3. And because h1, h2, and h3 are independent, so the probability of these 3 intersection set is the probability of each event and multiply together. And now, what is the probability of the complement of h1? Okay, so it's a 3, no, it's a 5 over 6, right? This one also 5 over 6. This one also 5 over 6. So we have 3, 5 over 6 multiplied together, and we have 5 cup over 6 cup. Okay. Now look at the case x equal 1. X equal 1 means that in the 3 times we told the dice that is only 1 times that is so 6. So there are 3 different cases. In the first case, so the first time so 6, and the second and the third time don't so 6. And similarly, in this case, we have only 6 at the second time. And in the third case, we have 6 at the third time. And because the independent property of x, h1, h2, and h3, we have that the probability of the intersection equals the probability of each event multiplied together. And here, so we obtain that the probability that x equal 1 is 3 times 5 square over 6 square times 1 over 6. The case x equal 2 also similar. And the simplest case is x is 3. This probability is 1 over 6 cubed. Okay. So in general, we have the following definition. A child with only 2 possible outcomes is called a binary child. So for example, we have male or female, we have failure or success, we have pass or fail when you take an exam. So there are only 2 possible outcomes. And to make it simple, we suppose that one outcome is success and the other is failure. A random experiment consists of n binary trials such that the first, the choices are independent. The second, a trial results in only 2 possible outcomes. Okay, labeled as success and failure. And the third is that the probability of success in a trial denoted by P is constant. It doesn't depend on the trial you take. And let's denote by X the number of trials that is success. Then X have a binomial distribution, and we can compute that the probability that X, capital X, equal to some small x is n to x times p to power x times 1 minus p to power n minus x for any x from 0 to n. Okay, so in the previous example, we have how many tries we have in this example? Okay, so in this example, we have 3 trials, and the probability of a success in that trial P is 1 over 6, right? So if you apply this formula, you will see we will have the same result here. And we denote the binomial distribution by B and P. And okay, so B stands for binomial, and sometimes. And the binomial distribution have 2 parameters. The first one is n, is the number of trials. And the second one is P, is the probability of success in a trial. There are many examples of binomial distribution. So for example, a one machine tool produce 1% defective parts, and let X be the number of defective parts in the next 25 parts that the machine produce. Then what is the distribution of X? So X will have the binomial distribution with parameter n is 25, and the probability of success P now is 0.01. Okay, because here we consider the defective part. So if we can find a defective part, it means that we are success. Okay, so there are 5 other examples in the slide, and I hope you will study it all by yourself. For each example, please find the parameter of the binomial distribution. Now we show the expectation and variance of the binomial distribution, and we can prove that if X have binomial distribution B and P, then the expectation of X is NP, and the variance of X is NP times 1 minus P. Okay. So you can see how to prove this in the textbook. I will skip it.